So we are continuing on our journey through Dalton's Law worksheet here, and I asked you to do number 2 and number 4. So I'm going to do number 4 first, okay? And let's get started. So a mixture of gases contains 0.75 moles of nitrogen, 0.3 moles of oxygen, 0.15 moles of CO2. And I'm in a tank or some kind of flask or container, so I like to draw, and I have 0.75 moles of nitrogen, and I have 0.15 moles, notice I'm keeping the E off because I'm cool, of CO2. Why I jumped to CO2 is beyond me. And I have 0.30 moles of O2 in this flask. Okay, total pressure, or PT, so pressure total, is equal to 1.56. So this looks a lot like the problem we did previous, which is number 3. Except instead of giving you grams, I gave you moles. And when I had grams, which was a how heavy number, we converted to a how many number by converting to moles. Because we know that moles is proportionate to pressure. More particles, more pressure. But since I'm already in moles, it seems to me all I got to do is divide by the total moles and get a mole fraction directly, since I don't have to convert here. It should be clear I don't have to convert from grams to moles because I have grams already. But the one little difference in this problem is that these 3 gases collected in this container were all collected by water displacement. Now what does that mean? That means we took some kind of flask, let's just say a eudiometer tube or some kind of big container, like a upside down, let's say graduated cylinder. We filled it with water. Well, we filled it with water right side up. We put our hand, okay, I'm not really a great artist here, but put my hand underneath it, as my thumb, okay, and covered it, and then we took our flask, I should say, first, if I'm confusing you, okay, like a graduated cylinder, so to speak. We filled it with water. We turned it upside down. We put our hand on it, turned it upside down, and then we put this into a water bath. We put our hand under the water. We let go, and what we were left with, okay, is a flask filled with water. And the reason why the water doesn't come down, because, well, atmospheric pressure is keeping it up. In fact, we would need a tube, as we've talked about previously, about 34 feet or higher, okay, for the water to start coming down. So the water is being pushed up against, because the water is so light, the weight pushing down is nothing compared to the force pushing down by atmospheric pressure, because water is so light. Again, we need 34 feet of it to start competing with that force pushing it down, which is really pushing it up. So we have this tube here that is inverted and has water being pushed up into it. And then we're going to have some kind of flask or something, some kind of chemical reaction with a stopper probably and a tube. And we're going to generate, now the tube shouldn't get as thick down here, but we're going to generate some kind of gas, okay, from the chemical reactions, and that gas bubbles, those are not teardrops, those are circles, that bubbles would go up and it would push this water down, as I showed you before, okay, and you'd wind up having a flask eventually filled with gas, okay, and you change this gas generating reaction a couple different times to get your 3 different gases, okay, and that's collecting a gas over water. It's a nice easy way to make sure that all the gas goes into my flask here, and I can actually measure the volume, the space it takes up as it pushes water down, displaces the water. But one issue with water displacement is that you have, well, not only the gases that are trapped at the top here, but you also have water vapor. Since you're catching it over water, we know that liquid water evaporates at all temperatures. So you also have some water vapor in here. So as soon as I said I collected the gases over water, not only do I have these 3 gases, But the big elephant in the room here is I have water vapor here as well. So that there is 4 gases in my container. Okay, so I'm going to get rid of all of this so I understand the setup. So to solve for this problem and know what the partial pressures of each gas are, I have to understand that the total pressure, okay, PT is equal to the partial pressure of the N2 plus the partial pressure of the CO2 plus the partial pressure of the O2 plus the partial pressure of the water. Okay, so a nice easy way to get rid of this elephant in the room, which is the water vapor that is being created by the evaporation of water over the liquid through the water displacement method, is to look up its vapor pressure. Now, from a table, okay, and we would have this table available to us, and it's a vapor pressure table, kind of like table H for our Regents chemistry kids. Okay, we can look up a temperature and get the vapor pressure. So they're saying at 40 degrees Celsius, the vapor pressure is equal to 55.3 torr. Now that vapor pressure is the partial pressure. Now we could plug that in and solve for these 3 and continue on our merry way. All right, but since we're starting with moles, okay, it would be very difficult to have that pressure there. So what would make things easier is if we can just subtract out this value from this total pressure. And so what we need to do is convert the 55.3 into atmospheres. So 55.3 torr, and you should know this already. To get rid of torr, torr goes on the bottom. Torr is for Torricelli, so I should write capital. Okay, it's also millimeters of mercury. That's what he did, the first barometer to solve the problem that we talked about. And we know that there's 760 torr for every 1 atmosphere. So we're going to convert this to the same unit. Okay, I'm going to put this in my calculator, and I'm off and running. At least I'm sitting here doing this. 55 divided by 760, and I get 55.3 divided by 760, and I get 0.0728, we'll say, atmospheres. Not large, but certainly adds to it. So what I'm going to do with this is I'm going to subtract this partial pressure. This is the partial pressure due to the water vapor. So I'm going to subtract that from the total pressure. So 1.56 atm is the total pressure of all 3 gases. Well, I know the pressure of the water from my tables, my vapor pressure tables, or my table H. I can look it up because vapor pressure is directly related to temperature. Higher temperature, more molecules have an energy to escape the gas phase. So I subtract, now that I'm in the same units, 0.0728 atmospheres. We're going to find our new pressure total without the water. So I'm subtracting out the water pressure. That's what you do in these problems. Minus 0.0728. And I get a new total pressure is 1.4872. So my new, okay, pressure is 1.4872 atm after I subtract out the water pressure, the partial pressure due to the water vapor. Okay, so what do I do here? Well, same thing. Now that we're going to rock and roll here, we're going to take our 0.75 moles and let's go find total moles. So we're going to add up all these moles. So when you put these in your calculator, 0.75 plus 0.15 plus 0.30, what I get is NT, which is moles total, okay, is equal to 1.2 moles. Now why do I do that? Because I want a what? Pressure fraction. Okay? So NT equals 1.2. So let's put this somewhere else that's in our way. So NT equals 1.2 moles. Okay, so for N2, we have 0.75 moles over 1.2. That, my friends, is a mole fraction. Fraction of the moles, fraction of the pressure. So I times it by the total pressure, which has been lowered because 1.4872 atm. Pressure has been lowered because we took away the water that was evaporating into our gas. So take our mole fraction, 0.75, divide by 1.2, and if you want that number first, you can. That's 0.625. And what this expression means, about 62.5% of all the molecules is due to N2, which means 62.5% of all the pressure is due to N2. That's how this works. So take this number, times it by my total, to find out the exact partial pressure. Okay, and I get oops, got a doohickey there, sorry. I get 0.9295 atm. Moles cancel. Okay, next one. CO2, 0.15 mole over total moles in the flask. That's my mole fraction. And then times it by my total pressure for the moles of atoms that I'm working with, and put that in your calculator. 0.15 divided by 1.2 times 1.4872. In any case, I get 0.1859 atmospheres. Y, moles cancel. Last one, 0.3 mole over the total, because my fraction of moles, I'm going to times that by my total pressure of the three gases that I'm talking about. Put that in our calculator, 0.30 divided by 1.2. That's 0.25 or a quarter. So we're going to find a quarter of that number times 1.4872. And I get 0.3718 atm. And what were they looking for? I think they just wanted the what? What is the partial pressure of each component? Let's just convert this to the correct number of sig figs. Look at my numbers. 40.3 is 3. That has 2. That has 2. That has 2. I don't consider this 40 because this is from tablature, okay? So actually it's 40.0 anyway. So it looks like 2 is the least significant number. So this becomes 0.93 atm for the nitrogen. This becomes 0.19 atm for the CO2, and this becomes 0.37 atm. And if you add these guys up, and these are your answers, they should equal approximately your total pressure. Right? Part equals whole. Dalton's law states if you take 0.93 times what? 0.19, 0.37. Let's put that in for fun because I can't wait to have fun. 0.93 plus 0.19 plus 0.37, and you get 1.49. And you say, Mr. Grodsky, it's 1.48. Well, it rounds off to 1.49. Okay, right here. So the part total pressure is equal to the individual partial pressures. And because of rounding, it's not exactly correct, but 1.49, that rounds off to 1.49. Okay, so here is your answer to number, what number is this? I don't even know. Number 4. Okay. And again, very similar to what we did above in this question. Looks like I wrote neater. Except we had to subtract away the water vapor. Okay. So we're going to start in a second on number 2. I'm going to take a short break. I'll be right back. Okay, I'm back. That was fast, right? Yeah. Okay, so number 2. And here we go. Hydrogen was collected in a eudiometer tube. Now, a eudiometer tube is nothing more than a fancy name for a big test tube that we use to collect gases over water. So it was collected in a eudiometer tube, which means we had a tube, okay, long skinny tube, which by the way is calibrated from 0 to 1, so you're actually measuring how much gas will fill this up. It was filled with water, okay, and we filled it entirely with water, and we filled it, I guess, with a water, and I guess my water's red here, and I guess my water should be red in here too. It wasn't mercury. Mercury's not red anyway. Any case, it was totally filled, so let's fill that all the way up. And then we bubbled by generating some gas in here, and we pushed some water out. Okay, and what's in here, of course, is hydrogen gas. Okay, but since we collected it over water, we got hydrogen and we've got water, because water is always evaporating. And we know the temperature of the water, okay, was 29 degrees Celsius. And that's important because it tells me exactly, okay, what kind of vapor pressure water has at that temperature, since water is always evaporating. So we have water vapor and hydrogen in there. My gosh, we have a mixture of gases in a container. It might have something to do with Dalton's Law of partial pressure, and it does. Okay, now, it was impossible to level the outside of the water with that of the tube, so the water level inside the tube was, okay, was 48, let's just do different terms. So the difference between this height and the height, oops, sorry, this height, sometimes my fingers are too big, so the difference between this height and the height above the water, we said, was 40.8 millimeters. Of course, this is water in the tube. We know why it's water's in the tube, because atmospheric pressure, okay, is pushing on the liquid, and you can think of this pushing as pushing the liquid up into the tube. So atmospheric pressure is supporting 48 millimeters of mercury, okay, and there's gas in here. So if you haven't figured this out, we've got a level of fluid and we have some gas in here. What you have, my friends, is a manometer. Yes, we're bringing back manometer problems. Yes, a manometer appears, or for sexist, a manometer. So what the question states is, okay, if the barometric pressure outside pushing down was 730, okay, millimeters of mercury, which is the same thing as torr, all right, knowing the vapor pressure in a handbook coming up, it's the red mark here, is 30.0 millimeters of mercury. What's the pressure of just the hydrogen in this area right here? Okay, well, we do know that the total pressure, PT, is equal to the partial pressure of the hydrogen plus the partial pressure of the water vapor. Now, I tell you what I do know. I do know because the water is at 29 degrees Celsius, and its vapor pressure, its force or gases produced at this temperature, is fixed at 30. Higher the temperature, higher the amount of gas produced by water evaporating. So this is found to be millimeters, and I forgot to add this, millimeters of mercury. So what we're saying here is that the partial pressure is 30 torr. That must mean, because we collected gas over water, that in this little container, top of the tube, where the two gases were collected, okay, there is a partial pressure of 30 torr. Okay. I still don't know what the total pressure is, and I'm trying to find hydrogen. So I have two unknown variables. So in order to find this, which is my answer to the entire question, I'm going to have to find the pressure total. So this is a manometer problem. Look very carefully. Okay, think about having a gas in a container in a U-tube. And here's our hydrogen. And here's our water vapor. And you notice, is it winning or is it losing? Well, clearly atmospheric pressure is pushing this water up, and clearly this gas is pushing down. Okay, so if we get rid of this arrow here, you'll see that the competing forces are the hydrogen and water pushing down. Oops, don't like that. Okay, that's the hydrogen and water is pushing down. Atmospheric pressure is actually, I know it looks like it's pushing down too, but it's pushing the liquid up.
Mrs. Doyle, please.
So atmospheric pressure is actually forcing this liquid up. So if I was to draw the tube over here again, just so you can see what's going on, we have the liquid in the tube. Okay, what are the competing forces? Well, clearly we have the air pressure pushing down on the liquid. And then we have this liquid which has a weight. It's pushing down too. So we have the what? The pressure total from the two gases pushing down. We have the weight of the water pushing down.
Basketball.
Then we have atmospheric pressure pushing and keeping the water up, and I'm going to show that as a different arrow because I can. And even though it's pushing down on the liquid, it's pushing the liquid up. That arrow goes up. Okay, and I know that force. That force is 730 torr. Okay, so my gosh, this two forces have to equal each other. So the total pressure is 730 opposing these two. Now, I don't know this pressure total, but can I work out the weight of water into torr? And you can. Before I do that, let me explain this another way. I have my gases. My gases are losing the battle of the fluid here, as we talk about. It's losing by how much? Well, if I was to measure between these two lines here, it's losing by 40.8. My atmospheric pressure pushing down is what? 730 torr. And the weight of the water is pushing down. So I've got the gas pushing down, and I've got the weight of the fluid pushing down, and this, of course, is pushing up. So we would say that the gas in the manometer is losing by the atmospheric pressure by this difference. So you know that this is pushing on the water, and this is winning by 40.8 millimeters of water, which is not a pressure equivalent unit that we use. So whether you think about the problem in this fashion, or you can see it in the tube, the bottom line is we got to convert this 40.8 millimeters of water into millimeters of mercury. Okay? So in order to do that, we use a very famous height times density, an inverse relationship equals height times density. Okay, we're going to convert it to millimeters of mercury. So I already have it in millimeters. That's kind of nice. So my 40.8 millimeters of water, density is 1 gram per milliliter. Okay, the height we want for mercury, the density is 13.6 grams per milliliter. And you solve for H, this would go to the bottom, so grams per milliliters would cancel, and you're left with some value that is 13.6 times smaller. That makes sense because the density, okay, is 13.6 times higher. So in any case, we've dealt with this before, 40.8 divided by 13.6, and what I get is the height for mercury would be 3 millimeters of mercury, okay, which we should know is another way to measure torr. So that's 3 torr. So this equals 3 millimeters of mercury. So the gases here are losing to the atmospheric pressure by 3 torr. This is 730 torr. So the pressure in here must be, you've guessed it, 727. Or look over here. Okay? If the pressure total, okay, or you can say the pressure here is losing by this difference here, which is 3 torr. So it's 730 pushing up. It's got to be 730 pushing down for this level to stay constant. So if I know the weight of the fluid in mercury is 3 torr, 3 plus what is 730? 727. So pressure total, my friends, in chemistry is 727 torr. Make sure you get your units correct. My partial pressure due to my water vapor, okay, is 30.0 torr. Okay? So what must be the partial pressure if all the individual pressures equal the total? Well, that's pretty simple. 727 minus 30, right? I'm solving for this value. I know the total because I solved it in the manometer problem first. Then I'm using Dalton's Law second, using the idea that when we collect gas over a dry liquid, we have a what? A vapor pressure of water at a particular temperature has its own unique partial pressure. So 727 minus 30, and that's our answer. And of course, this is equal to, okay, let's change it, orange, okay, 697 torr. It's a nice problem, and we're going to visit these. Okay, you may say, well, Mr. Grodsky, what about sig figs here? All right, well, 3 sig figs, 2 sig figs, 2 sig figs, so I guess this can become 7.0 if I care to. 7.0 times 10 to the 2, I need 2 sig figs, okay, torr. Okay, I'm not really concerned about the sig figs right here, the process. You should recognize that we first did what? We first did a manometer problem. From the manometer problem, we realized the height had to be converted into millimeters of mercury. Then from that point, what did we do? We found the millimeters of mercury, okay, and we subtracted, we did the manometer problem still, and we got the 727 total what? Torr. And then the last part, from the manometer problem and converting our height into mercury, it led us to the total pressure, and then finally we did the Dalton's Law part of the problem. So there's 2 parts of this problem. I'm going to call them 3 again. The first part, again, the manometer. In the manometer, we had to convert the column of water into mercury into a unit we can use. And then once we had that value, we went back into Dalton's Law of partial pressures. Hope you enjoyed, as I did.